What is up, young chemists? Mr. Rosen here. How's it going? Hope you're doing well. This video is going to be a bit of a long video, so I encourage you to maybe watch it in sections or pause, maybe watch the first half of it as we're covering that part in class, and then watch the other parts later. But you can see here it says that we're going to cover all of nomenclature, so that's all of naming. We're going to discuss the idea of a polyatomic ion, and we're going to practice forming neutral compounds. So if we're looking at how two atoms will combine to form a molecule, or an atom and a polyatomic ion, how many of each will there be in the neutral compound? So we'll get started here with nomenclature. So actually, I'm sorry, we're going to get started with just forming the basics of neutral compounds, because when we are going from a name to a formula, from a formula to a name, we need to know how to form a neutral compound first. So as it says here, in order to understand how compounds are named, you first need to be introduced to the idea of bonding. So during bonding, atoms either share or transfer electrons. With positively charged ions and negatively charged ions, these are forming ionic compounds. It's typically a metal is positively charged and a non-metal is negatively charged. The metals tend to lose one or more electrons to become positively charged, and the nonmetals tend to gain one or more electrons to become negatively charged. And then those two ions will interact, and when they interact, they will form the simplest neutral compound. Okay, so here's a table, and in the missing space, I'm going to write the formula for the neutral compound that will form when these two ions interact. So just to jump, this is potassium ion, it's +1, and this is a fluoride ion, it's -1. You usually write metal and then non-metal, or positive and then negative. So we have K and we have F. Now, K has a +1 charge. F has a -1 charge. So if this is +1 and this is -1, those two charges cancel out, and this is a neutral compound. That's the simplest neutral compound that can form. So just one of each. Pretty straightforward, pretty simple. Now in contrast, on this one, if we have potassium, K, and then we have sulfur, S, we think, is that a neutral compound? Well, K has a +1 charge, and sulfur has a -2 charge. So if this is +1 and this is -2, does that give you a neutral compound? No, it's not neutral. You're going to need 2 potassium ions in order to balance out the -2 charge of the one sulfur. Okay, so if this sulfur is -2, you need to have 2 positive charges. So that means you need 2 potassiums. So I'm going to put a 2 down here. That's K2S. The 2 Ks, each K is +1, so if you have 2 of them, that's +2, that balances out the -2. Okay, so we're going to continue that thinking over here. If we have K and we have N, is that a neutral compound? K is +1, N is -3. So it's not neutral. We're going to need 3 Ks in order to balance out the -3 charge of the one nitrogen. These are all neutral compounds. They're the simplest neutral compounds you can form between these two ions. Okay, now this one here, we have calcium, metal, and then we have sulfur, non-metal. Now, the calcium is +2. The sulfur is -2. So guess what? That's a neutral compound. +2, -2. Overall gives you 0. Here we have Ca, and then we have F. Is that neutral? Calcium's +2. Fluoride is -1. +2, -1, that's not going to be neutral. You're going to need 2 fluoride ions. So you put a 2 here. +2, and then you have 2 fluorides, and each fluoride is -1, so that's -2. That is a neutral compound. This is the idea of forming a neutral compound. Now this next one's pretty confusing. You have calcium, Ca, and then you have nitrogen, which is N. Calcium's +2. Nitrogen's -3. So, if you had 2 calciums, that would give you +4, and then still -3. So that doesn't help. So maybe you put a 2 here and a 2 here, then that's +4 and -6. You can see you might go back and forth a couple times. It's a lowest common multiple thing between 2 and 3. The lowest common multiple is 6, right? So if you take 2 times 3, you get +6. If you take 3 times 2, you get -6. So we're going to have 3 calciums. Okay, 3 times 2 is +6. And we're going to have 2 nitrogens, because 2 times -3 is -6. +6, -6. That's the simplest neutral compound you can form between those 2 ions. Again, we're going to maintain integers for our subscripts. Sort of a similar thing here. We have aluminum, and then we have sulfur. Aluminum is +3, sulfur is -2. So if you have 2 aluminums, that gives you +6, and 3 sulfurs gives you -6. This is Al, and then we have F. Aluminum's +3, fluoride is -1. +3, -1. You need 3 of these, so that you have +3, -3. And then here we have aluminum, which is +3, and nitrogen, which is -3. That is a neutral compound. So this is the idea of forming a neutral compound. It's important because if you go from, if you read a name, you need to be able to write the formula. Or if you see the formula, you need to be able to write the name. And the compound is going to be a neutral compound. So you have to be able to form neutral compounds in order to do it correctly. So now let's get into naming, nomenclature. This is our first type. We're going to have 3 types of compounds: type 1, type 2, and type 3. Type 1 is an ionic compound, which means a metal and a nonmetal. Okay, metal and a nonmetal. Now, the metals make up about 75% of the periodic table. This periodic table doesn't have the sort of dark stair-step line on it, but your version of the periodic table probably has a dark line that sort of zigzags down the periodic table about here. Okay. And these are nonmetals. Everything else, all of this, these are all metals. Okay, these are metals. Now, a type 1 metal, actually, I guess hydrogen's not really considered a metal, but it's over here. A type 1 metal, the metal is in column 1 or column 2. There are a couple of exceptions, which are over here. They are silver is always +1, zinc is always +2, and aluminum is always +3. So there's a little staircase right here. Aluminum, zinc, silver, +3, +2, +1. Those are included in type 1 metals. But the metal is either in column 1, column 2, or is aluminum, zinc, or silver. The metals are always from that section. That's a type 1 metal. And then it's combining with a nonmetal. And naming them is very easy. All you have to do is named the cation. The cation is the positively charged ion, which is the metal. And then the anion is the negatively charged ion, which is the nonmetal. And you change the ending of the nonmetal to "ide." So a very common example of this would be something like NaCl. And you might say, oh, NaCl, I've seen that before. That's salt, right? That's salt. Well, it is what's called a salt, but it's, table salt. If you look on the periodic table, Na, sodium, it's a metal. It's in column 1. And then you have chlorine, which is a nonmetal. So this is a metal and a nonmetal. It's a metal and a nonmetal, and the metal is in column 1. So this is what's called a type 1 compound. Type 1. When you're naming it, you name the metal, which is sodium. That's the cation. And then you name the anion. This is chlorine. But you change the anion ending to "ide. So it's not sodium chlorine, it's sodium chloride. Oh, sodium chloride, salt, NaCl. You use that, probably use that in your daily life frequently. So here, another example, it says when strontium and chlorine combine, they form a neutral compound by combining 1 strontium and 2 chlorine ions. So this is a neutral compound. What is the name of the compound? You name the metal, the cation, strontium, and then you name the nonmetal, chlorine, with the ending changed to "ide. Chloride. Strontium chloride. We don't need to worry about the 2. The fact that it's strontium means it has a positive 2 charge. Because a little recap, a review of the periodic table, if it's in column 1, it's going to have a +1 charge. If it's in column 2, it's going to have a positive 2 charge. So the fact that it's strontium means it has a positive 2 charge. Also, the halogens, which is here group 17 on this periodic table, it's also 7A on a different periodic table. The halogens have a charge of -1. So if chlorine has a charge of -1 and strontium has a charge of +2, the only neutral compound that could form would be this one. So when you read strontium chloride, you can figure out how many of each there is based on their placement in the periodic table. So that's a type 1 compound. The next type of compound is type 2. Now, a type 2 compound is also a metal and a nonmetal. However, the metal is not coming from group 1 or 2, including zinc, silver, and aluminum. So type 2 metals are coming from other parts of the periodic table. So, most of the type 2 metals you're going to find somewhere in this middle part of the periodic table. Okay, now, as I just mentioned, if the metal's in column 1, it has a charge of +1 every time. If the metal's in column 2, it has a charge of +2 every time. These metals in the rest of the periodic table often form multiple different charges, depending on what they are interacting with. So here you can see some examples. Iron, sometimes it's +3, sometimes it's +2. Copper, sometimes +1, sometimes +2. Cobalt, tin, lead. They form different charge ions. Now, you have to specify what the charge of the ion is. Okay? So for example, quick example, and I actually have this in your lesson, but well, let's do it with copper. So if you had CuO, oxygen has a -2 charge, and in this case, Cu has a +2 charge. So we have CuO. And if you were to name that, you would probably say copper, and then the nonmetal with the ending change "-ide. So oxygen becomes oxide, so copper oxide. But what if you had Cu2O? That would be a copper with a positive 1 charge. Oxygen still -2. So these are both neutral compounds. And if you were going to name this, you'd say, oh, well, that's copper, and then oxygen becomes oxide, right? They're both copper oxide. Now, hopefully you see that that's an issue. These have different formulas. They can't have the same name. So you have to specify what the charge of the metal is. And to do that, we use Roman numerals. And the Roman numeral tells you the charge of the metal. In this case, oxygen's -2, copper is +2. This is a neutral compound. So we write copper, and then we're going to have the Roman numeral 2 in parentheses, oxide. This is called copper 2 oxide because the charge of copper is 2. In this case, oxygen's -2, copper has to be +1. So this is copper 1 oxide. Copper 1 oxide, copper 2 oxide. Notice, the Roman numeral is not how many coppers you have, right? You might think, well, hold on, how come this one's copper 2 and this one has 2 coppers? And this one's copper 1, but that one has 1 copper. It's not about how many coppers you have. It's the charge of the metal. That's what the Roman numeral means. Okay? So because type 2 metals can form multiple charges, you have to specify the charge using a Roman numeral. So here is an example problem. Another example problem. I just did a couple there. So it says, when lead and chlorine combine, they form a neutral compound by combining 1 lead with 4 chlorines. The formula is PbCl4. What is the name of this compound? Well, Pb is lead. Cl is chlorine. Chlorine becomes chloride. Now, lead, if you look on the periodic table, it's not in column 1, it's not in column 2, and it's not aluminum, zinc, or silver. Lead is over here. Okay, it's under the staircase separating them. It is a metal, but it's a type 2 metal. And lead can form, +2 charge. It can form a +4 charge. You have to specify what the charge of the lead here is. Okay, because what if you had PbCl2? That also exists, right? That would also be lead chloride. So how do you specify the difference between them? Well, chlorine has a charge of -1. If chlorine has a charge of -1 and there are 2 of them, right, this is a neutral compound. You can see there's no charge written anywhere. It doesn't say +1 or -1. There's no charge, so that means it's neutral. If this is a neutral compound and there are 2 chlorines, each chlorine has a -1 charge. So this is a -2. Pb has to be +2. So this is lead 2 chloride. Now here, if this is a neutral compound, and it is because you can see there's no charge written anywhere, chlorine has a -1 charge. It's in the halogen family, column 17 or column 7a, depending on your periodic table. Chlorine has a -1 charge. If there are 4 chlorines here and each chlorine is -1, the charge of the Pb must be +4. So this is lead, Roman numeral 4, in parentheses, chloride. 5 is a V. This is 1 before the V. So 1 before 5 is 4. This is 4 in Roman numerals. So these are naming type 2. Naming type 2 compounds are the most complicated ones. Okay, so type 1 and type 2 are both a metal and a nonmetal. In type 1, the metal is in column 1 or 2. Also included are aluminum, zinc, and silver. And all you have to do is name the metal and then name the nonmetal with the ending changed to "ide." For type 2, the metal is not in column 1 or 2. And again, you name the metal and then you name the nonmetal with the ending change to "-ide", but you also have to include a Roman numeral to specify the charge of the metal. Now, in contrast to those, we're going to talk about type 3, and then we'll do practice with them, okay? So a type 3 is different than the others because it contains only nonmetals, so nonmetal only. These are referred to as covalent or molecular compounds. They're made of only nonmetals. So that means that the elements in them are going to be coming from, basically this part of the periodic table, mostly this part of the periodic table. Maybe hydrogen's included in there too, okay? Like that. So let's think about how this one works. There's a system of prefixes, and the prefix tells you how many of that element you have. Now, mono is 1, di is 2, tri is 3, like a triangle. We have also tetra, penta, hexa. Tetra is 4, penta is 5, like a pentagon, pentagram. Hexa is 6, hexagon. Hepta 7, octa 8, octagon, octopus. 8 sides, 8 tentacles. Nona is 9, and deca is 10, like decade. Okay, so those prefixes are used to tell you how many of each element you have. Okay, now for naming type 3 compounds, a couple of rules here. You name the first element using the full element name. Then you name the second element as though it were an anion, so you do change the ending to "-ide" again. You use prefixes to denote how many of each atom you have present. Mono is not used on the first element. So if you have one of the first element, you don't say mono. But if you have one of the second element, you do say mono. So in this example, you have 1 carbon and 1 oxygen. It's not monocarbon monoxide. It's just carbon monoxide. Carbon is the first element, and then you have 1 oxygen. Oxygen is oxide, so monoxide, monoxide. Sometimes when you have consecutive vowels, you drop one of them, but don't worry about that too much. So here we have S and O2. S is sulfur. Move this up. S is sulfur. You do not say monosulfur because it's the first one. You just say sulfur. And then oxygen is the second one. Oxygen is oxide. You change the ending to "-ide. It's not sulfur oxide. It's not sulfur monoxide. How many oxygens are there? There are 2. What is our prefix for 2? Di. So this is called sulfur dioxide. Okay, in your daily life, you've probably seen CO2 before. What's that called? Carbon, because that's the first one, and then you have 2 oxygens, carbon dioxide. Have you heard of that? Global warming, CO2 emissions, carbon dioxide. That's how the naming system works. Okay, da-da. Now you are ready to attack the nomenclature game. We're going to have type 1, 2, and 3, all of them, type 1, 2, and 3, practice here on the bottom of the page. First, we're going to practice going from a formula to a name, and then we're going to go the other way around, okay? So, I'm going to have this here. If you want to pause for a second to try naming these compounds, go ahead. And in just a second here, I'm going to go over the answers. So pause the video, try to solve them, and see how you do. Okay, let's solve. Mg and O. First thing you want to do is find them on the periodic table. Mg is in column 2 on the periodic table. So not only does that mean that it's a metal, that also means that it's a type 1 metal. It always has a charge of positive 2. So this is going to be a type 1 compound. We also have oxygen over here, which is a nonmetal. So this is a metal and a nonmetal, and the metal is in column 2. So this is a type 1 compound. Naming type 1, you name the metal magnesium, and then you name the nonmetal with the ending changed to -ide. Oxygen becomes oxide. We do not need any Roman numerals. Roman numerals tell you the charge of the metal, but because magnesium is in the second column, it's always positive 2. We don't need a Roman numeral because that would be redundant. The fact that it's magnesium tells me it has a positive 2 charge. So magnesium oxide. Sweet. Let's do the next one. CrCl3. Again, you're going to find them on the periodic table. Now, chromium is right here on the periodic table. It's a metal. Now, is it in column 1 or column 2? No. And it's also not aluminum, zinc, or silver. So chromium is a type 2 metal. And it is combining with chloride, which is over here, a nonmetal. That has a -1 charge. Okay. This column called the halogens, the second from the right, these are all -1. So it's a metal and a nonmetal, and the metal is not in column 1 or 2A. So this is a type 2 compound. Type 2 compounds, you name the metal, chromium, and then you name the nonmetal with the ending changed to -ide, chloride. But with type 2 metals, you have to specify what the charge of the chromium is. Chlorine has a -1 charge, and there are 3 of them. This is a neutral compound. So if there are 3 chlorides, and each is -1, the charge of this one chromium must be +3. 1, 2, 3. That's going to be a Roman numeral inside of parentheses. Chromium 3 chloride. Let's go. Okay, next one. We have sulfur, and then we have nitrogen. Looking on the periodic table, sulfur is right here. That's a nonmetal. And nitrogen's right here. It's also a nonmetal. Okay, this is kind of the separating line between metals and nonmetals, sort of like this. And if the element's along the line, it's probably a metalloid, which has properties of both. But these are definitely nonmetals. So we have 2 nonmetals. If it's all nonmetals, that means it's type 3. So type 3 means we get to use our prefixes. Di, tri, tetra, hexa, mono, that kind of thing. So we have sulfur. So I'm going to write sulfur. Now, if it was just 1 sulfur, then we'd have it as sulfur. If it was 2 sulfurs, then we'd write disulfur. We have 4 sulfurs. The prefix for 4 is tetra. So I'm going to write tetrasulfur. Tetrasulfur, that means 4 sulfurs. And then I have 4 nitrogens. Now, nitrogen is a weird one. You go, oh, is it nitrogenide? It's just nitride. So nitrogen with an ide is nitride. And we have 4 of them. So it's tetra. Tetrasulfur, tetranitride. It's a weird one, but that's what it is. All right, we're moving on. Next one, we have carbon. And then we have bromine. Now, I pause there for a moment because carbon is a nonmetal and bromine is also a nonmetal. If you look over here on the periodic table, bromine is right here, carbon's right here. These are both nonmetals. So they're both nonmetals. That means, again, this is type 3. We just have one carbon, so I'm going to write carbon. Okay, it's not monocarbon, it's just carbon. And then I have bromine. Bromine becomes bromide. What's happening, bromide? And then you have 4 of them, so it's tetrabromide. Carbon, tetrabromide. Carbon and 4 bromines. This is a D, make sure bromide. Okay, we're chugging along. This is a combination of all 3 types of naming. If you're in my class, you know that I've broken this down into sections. So there is a type 1 practice section, and there's a type 2 practice section, and there's a type 3 practice section. In this video, I'm explaining all 3, and then you have them all mixed together. And so you have to identify what type it is, and then apply the naming rules to it. So this is challenging. Barium chloride. Ba is in column 2. And so not only is it a metal, but it's a type 1 metal because it always has a positive 2 charge, and chloride is a nonmetal over here that has a -1 charge. So this is a type 1 compound, metal and a nonmetal. You name the metal barium, and then you name the nonmetal chlorine, but its ending is changed to chloride. I do not need to specify the charge of the barium because barium is in column 2 on the periodic table. It always has a positive 2 charge. So the fact that it's barium chloride, I know this is going to be +2, this is going to be -1, and I can know what the formula is. Next we have SnBr4. Now you might be tempted to go, oh, well, this one is carbon tetrabromide, so is this one, whatever Sn is, tetrabromide, right? Sn on the periodic table. My periodic table doesn't have the names on it, but Sn is tin, 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 and it is a metal. So you might be tempted to go, oh, well, if this one is carbon tetrabromide, is this one tin tetrabromide? No, because you only use this naming system if it's type 3, which is non-metals only. Tin is a metal. So this is a metal and a nonmetal. And the metal is not in column 1 or 2. So that means that this is a type 2 compound. So we say the name of the metal, tin, and then we say the nonmetal with its ending changed to "ide," which is bromide. And then we need to specify what the charge of the tin is. Now, bromine is in column 17, or 7A on the periodic table. It's right underneath chlorine. It has a -1 charge. Bromine has a -1 charge. So if bromine has a -1 charge, and there are 4 of them, the charge of this tin must be +4. So this is a Roman numeral 4. 1 before the V, 1 before 5 is 4. So this is tin 4 bromide. Next one on here, we have sulfur and chlorine. Sulfur is right underneath oxygen on the periodic table, and it's also right next to chlorine. These are both nonmetals. So we have nonmetals only. Nonmetals only means type 3. And type 3 means prefixes, di, tri, tetra, hexa, hepta, mono. We have sulfur, so I'm going to write sulfur. Now we have 1 of it. I'm not going to say monosulfur, just sulfur. And then we have chlorine becomes chloride, but we do have 2 of it. The prefix for 2 is di, D, I. Sulfur dichloride. Okay, next one on here. We have magnesium and phosphorus. Magnesium, we actually saw earlier, it's in column 2. So it's a metal. And it's a type 1 metal because it always has a positive 2 charge. Phosphorus is right here as a nonmetal. Phosphorus has a negative 3 charge. This is -1, this is -2, this is -3. So this is -3. Anyhow, it doesn't really matter because we have a metal and a nonmetal, and the metal is in column 2, so it's a type 1 compound. Type 1. All you have to do is say the name of the metal, magnesium, and then say the name of the nonmetal with its ending changed to I. So is phosphorus phosphoruside? How does it go? It's just phosphide. Magnesium phosphide. Not phosphoride or phosphoruside. Phosphide. Okay, so you can check your answers. How did you do? Did you do well? Did you get some wrong? You have to identify what type it is before you name it. Okay, now what we're going to do, this is from the formula to the name. Now, I'm going to give you a bunch of names, like we have on this page, and you are going to write what the formula is. You've got to be able to go both ways with it. So, again, you're going to take some time. Okay, if you want to, you can pause the video and write down what your answers are here. So you can see that the names are given, and you have to figure out what the formula is. Remember, you're always forming neutral compounds. You have to form the simplest neutral compounds. So go ahead, pause the video, solve them. Okay. Iron, and then you have a Roman numeral 2. Now, immediately, if it has a Roman numeral, you know it's a type 2 compound. And that Roman numeral tells you the charge of the iron. Okay, so we have iron, which is Fe, and arsenide is arsenic. Arsenic on the periodic table is As, capital A, lowercase s. It's underneath phosphorus. And in a recent problem, just our last one, we said that, these are all -1, these are all -2, and these are all -3. Arsenic has a charge of -3. So, if arsenic has a charge of -3, and the iron has a charge of +2, you have to form the simplest neutral compound, which would be 3 of these and 2 of these. That's a hard problem to start off with. Just a heads up. That's Challenger. But this is why we practice. The next one, barium chloride. Or sorry, this is beryllium chloride, but it's the same rules, so no big deal. Beryllium is right here. Barium is down here, same column. They're both metals. It's a type 1 metal. That's why there's no Roman numerals here. Okay. Now everything in column 2 has a +2 charge. So Be is beryllium. That's an E. And then chlorine is Cl. Now, beryllium has a +2 charge. Chlorine has a -1 charge. So that's not a neutral compound. If this is +2 and this is -1, you need to have 2 of these to form a neutral compound. That's beryllium chloride. Silver is a metal, and it's a type 1 metal. So type 1 is everything in column 1 or 2. Also included are silver, zinc, and aluminum. Silver has a charge of positive 1. Oxygen has a charge of -2. So silver is Ag. Oxygen is O. If silver is +1 and oxygen is -2, this is not a neutral compound. You would need 2 silvers. So Ag2O. So a big part of going from the name to the formula is knowing the trends on the periodic table in terms of charges, right? So these are +1, these are +2. We don't have bonding with our noble gases, so that's 0. These are -1, -2, -3. And then the stuff in here is various charges, although aluminum is always +3, zinc is always +2, and silver is always +1. 3, 2, 1. Okay? Iron 3 bromide. So you have iron, which is Fe, and then you have bromide, which is bromine, which is Br. Now, here it tells you that the iron has a charge of +3. That's what the 3 means. It's the charge of the iron. And then bromine, it's on the periodic table right underneath chlorine. We've seen it a bunch so far today. It's -1. So if this is +3 and this is -1, in order to form a neutral compound, we have to have 3 of these. FeBr3. Next up, palladium 4 bromide. Palladium is Pd. It's here in the middle of the periodic table. It forms different charge ions, but this tells us that it's a 4. Now, bromine, we just had in the last problem, is Br. If the palladium has a charge of +4, bromine is -1. So to form a neutral compound, you need to have 4 of these. Next one, selenium hexafluoride. Now the fact that you see hexa, you know this is a type 3 compound. It's nonmetals only. Selenium is Se, and then hexafluoride. So that means you have fluorine, hexa. If you look on our chart, you can think about like a hexagon, but hexa is 6. So 6 fluorines. There it is. Next one, triboron. Tri, you can see that's a type 3. Tri is 3. So boron is B. If it's triboron, that means there's 3 of them. Silicon becomes silicide, I guess. Yeah, I don't know. I've never even really said that out loud, but you have Si. I think this is a mistake. If you only had one of it, this should be mono, right? So I think this is actually a mistake. I apologize, but if it was just one of it, then you would have a mono in here. There should be a prefix on that. 3, -9. Yeah, so I apologize on this problem. Don't worry too much about this. I have to go back and correct that. I think I either left off mono or whatever the prefix was supposed to be. although boron tends to be a positive 3, and so I'm not really sure exactly what this compound is. It's just supposed to be an example. Anyhow, let's move on. Manganese looks a lot like magnesium, right? You see that and you go, oh, maybe it's magnesium. Well, if it was magnesium, it would be a type 1 compound, and it's not, because you can see it has Roman numerals. It's manganese, which is actually Mn, which is here in the middle of the periodic table. It's a type 2 metal. So Mn, not Mg, Mn, that's manganese. And then you have nitrogen, which is nitride, which is N. Nitrogen has a -3 charge. This is saying that the manganese has a +4 charge. So if this is 4 positive and this is 3 negative, you have to do a common multiple thing, which is going to be 12. So you're going to have 3 of these and 4 of these. Okay, so it's harder to go from a name to a formula than from a formula to a name, but it's good to practice both. Now, as I mentioned, the video is a little bit long. It covers nomenclature, which we have been doing, type 1, 2, and 3. It also covers forming neutral compounds, which we've been doing. And the last part is talking about polyatomic ions and forming neutral compounds with polyatomic ions, or possibly naming with polyatomic ions. So a polyatomic ion is an ion made of many atoms. Okay, so poly means many, right? Monatomic would be one atom ion. So like if you had something like a calcium ion, that's monatomic. But a polyatomic ion has multiple atoms in it, and they're combined, and as a unit, overall, they have a charge. These polyatomic ions stay intact during chemical reactions, usually, and these are some of the most common ones. Okay, now in your textbook, you'll see probably a table that has maybe 24 of the most common polyatomic ions. I've put 7 or 8 here. I guess that's 7, and these are like the most common of the most common. You need to memorize these, okay? There's no way around memorizing them. The name and the formula and the charge, you just need to know nitrate means this, phosphate means that. You need to know what their charges are. Okay, so I encourage you in class, I have you make flashcards for these, and then I quiz you just on these, but knowing these polyatomic ions, so that it's something you don't even need to think about, can be really, really useful to you. So here it says forming neutral compounds and naming with polyatomic ions. Okay, when you have monatomic ions, like let's say sodium and chloride, it's just 1 to 1, right? Sodium is +1, chloride is -1. It's NaCl. The same applies for polyatomic ions. Okay. But if you have more than one of a polyatomic ion, it gets a little bit tricky, right? So like if you had Mg, which is +2, and you have chloride, which is -1, you would just say, okay, well, it's not MgCl, it's MgCl2, right? If you need more than one of this chloride, you just put a little 2 here. But it gets weirder with a polyatomic ion because the subscripts can sort of get in the way of each other. So let's look at naming and forming neutral compounds with them. So here it says the monatomic ion sodium is Na, and the polyatomic ion nitrate is NO3 negative. What is the formula of the neutral compound that would form between these? So you have Na, that's sodium, and then you have NO3, that's nitrate. Now, sodium is +1, and nitrate, this whole thing, is -1. So if this is +1 and this is -1, that's it. It's a neutral compound. And this is called sodium nitrate. All you have to do is name the metal and then name the polyatomic ion. You don't change the ending to "ide" or anything. It's sodium nitrate. Easy as that. Now, in contrast, what if we had magnesium, which is +2, and nitrate? So you have Mg, and then you have NO3. What's tempting, you can see here it says not, what's tempting to say, okay, well, I have magnesium, and then I have nitrate. Magnesium is +2. Nitrate is -1. So this is +2, this is -1. To form a neutral compound, I need to have 2 of these, right? I need to have 2 nitrates. So if I need 2 of them, I'm just going to put a 2 here. Can you see how that's confusing? What, do I have 32 oxygens? What is this, right? This is not correct. If you need to have more than one of a polyatomic ion, you put the polyatomic ion in parentheses, and then you put how many you need outside of it. So that means you have 2 of whatever is inside of the parentheses. Each nitrate's -1. If you have 2 of them, that means this is -2, this is +2, that's a neutral compound. And naming it, this would be simply magnesium nitrate. So to finish the video up, we're going to do a little bit of practice forming neutral compounds, just like we started this video with, but this time it's including polyatomic ions. Okay, so if you want to, take a moment and attempt to solve these. You're going to form neutral compounds for each, and then you can check your answer. I'm about to go over them in about 5 seconds. Okay. Always metal first and then non-metal. So these are cations, and these are anions. Cation, anion. So we have zinc, and then we have hydroxide, OH. Now we're forming a neutral compound. Zinc is +2. Hydroxide is -1. So this is +2, this is -1. This is not a neutral compound. We need to have 2 of these. Now ask yourself, did you just put a 2 here? If you did, that's telling you you have 1 zinc, you have 1 oxygen, and you have 2 hydrogens. That's not what you want. You want 1 zinc, and you want 2 hydroxides. That is the correct formula. Next we have zinc, and then we have sulfate. Now, zinc is +2. Sulfate, this whole part, is -2. +2, -2. Ta-da! That's it. No parentheses needed. Now this next one is a tricky one. We have zinc, and then we have phosphate. Zinc is +2. Phosphate, this whole thing, is -3. It's one of those common multiple things where we're going to need to put this in parentheses because we're going to need more than one of it. If this is +2, we're going to need 3 of it. That gives you +6. And if this is -3, you're going to need 2 of it. That gives you -6. So you can see that's a little bit confusing because you got to get your parentheses in there. But that's your simplest neutral compound. Next, we have iron, and then we have hydroxide. Iron's +3, hydroxide is -1. Again, it's tempting to say, all right, well, we need 3 of these to make a neutral compound. Well, don't forget, it's a polyatomic ion, so you need to put it in parentheses. This next one, it's sort of similar to this here. We have Fe, and then we have SO4. Iron is positive 3. Sulfate is minus 2. In order to form a neutral compound, I'm going to put this in parentheses. We need 2 of these. If I have 2 irons, that's positive 6. And if I have 3 sulfates, that's negative 6. Next, we have iron, and then we have phosphate. Iron is positive 3. Phosphate, which is PO4, is negative 3. So this is positive 3, this is negative 3. Ta-da! Neutral compound, just one of each. Next we have ammonium, which is a polyatomic ion as a cation. So we have NH4. That whole thing has a charge of positive 1. And then we have hydroxide, OH. That has a charge of minus 1. So positive 1, minus 1. Ammonium hydroxide. Done. Neutral compound. Next we have NH4, that's ammonium, and then we have a sulfate, which is SO4. Now, these are both polyatomic ions. This has a charge of positive 1. This has a charge of negative 2. So if we're going to form a neutral compound, you need more than one of these. So we're going to put this in parentheses and put a 2 here. That gives us plus 2 and balances out the minus 2. Finally, we have sort of a similar situation here. We have NH4, that's positive 1, and then we have PO4, which is negative 3. So we have ammonium and we have phosphate. And if I was naming this, it'd just be ammonium phosphate, straightforward. But this is plus 1 and this is negative 3. So I need to have more than one of these. So I'm going to put this whole thing in parentheses and I'm going to put a 3 here. That gives me 3 positively charged ammoniums to balance out the 1 phosphate polyatomic ion that has a charge of negative 3. So this has been practice forming neutral compounds with polyatomic ions, a little bit of naming with polyatomic ions, and it has also been a whole lot of nomenclature, which is naming. We did type 1, type 2, and type 3 compounds, and of course, as you can imagine, practice makes perfect. Make sure you're studying the periodic table, the charges of the different groups on the periodic table, and practice forming neutral compounds. Go from the formula to the name, go from the name to the formula. Good job. Rewatch this video, break it down into sections. Keep up the good work. This is Mr. Rosen. Out.